Now, when I was drawing the cyclic structure from this open structure that I have, so I had firstly got this open structure, and when I was drawing the cyclic structure from this particular structure, I was confused as to why I am keeping this CH2OH group at transposition. So what am I talking about? I'm talking about this CH2OH group which I am placing at transposition with this OH in both the cyclic structure. Now, why did I place it at the transposition? So, to understand this, what I'm going to do is I'm going to draw this structure in the Fisher form now. So, where do I begin? I just draw a straight line and I'm going to place the carbons one by one. So, I start naming my carbons from this. So, this is my first one, the second, the third, the fourth, and the fifth. And I'm going to draw them accordingly. So, this assumes the sixth number. I'm only talking about the carbons in a straight chain. So what do? I first place all of them. Since my CHO group lies at the top, I just place all of them. I'm gonna place my H and my OH at the bottom. So what happens is that when I start placing them, I'll just find out why it was was a necessity to place that OH and that CH2OH group in transposition to each other. So now I have here, what do I have? This CHO group that I had at the top will now come to this particular position and I've got my CHO group over here. Next, I have got this CH2OH which was lying at other end, and now I place this CH2OH group over here. So now I've got this structure. Now I start placing my H and my OH in their particular positions. So I said whatever is on the left stays on the left in this particular Fisher projection, and if this H is on the left, it comes on the left. So I get this H on the left, OH being on the right. Now I notice that in the second chiral carbon over right here, I have my OH at the left position. So it comes to the left now. So I've got my OH now on the left and my H on the right. And similarly, if I start doing it for everyone, so the left group comes on the left and the right stays at the right. Now I have this particular Fisher projection for this particular open structure that I was drawing. Now, in order to make that bonding appear, which bonding am I talking about? What I did was to make that closed structure that we are just talking about a lot, I took out some lone pair of electrons from this particular OH and I put them over here, where I took out some lone pair from here and I transferred them into that CHO group. To do that, and for that bonding to occur, this OH that I have over here needs to be rotated. Which OH? This one. This needs to come to the top so that I can form a closed structure that I was forming in these particular cyclic form. So what do is I have to make this OH come at which position? I have to shift this OH to this particular position so that the bonding between OH and this CHO occurs. So what I'm going to do next is I'm going to rotate. I'm going to start rotating, and when I draw my next Fisher form, I'll have a rotated CH2OH and OH positions. So now I have this exact same Fisher form, but what changes is that now my OH comes over here, and for that to happen, this CH2OH group will come to this position. Okay, and I have got my CH2OH at this position, and I'm left with an H which comes over here. Now, the rest of the valencies, that is fulfill of the rest of the chiral carbons, and I've got myself the same. I draw the OH was here, the H was here, the H was here, the OH was here, H was here, and the OH was here. So I'm drawing exactly the same as this one, but I'm just rotating my OH and COH, CH2OH, so that the bonding can occur between this CHO and this OH, because that is the cause of my cyclic structure. So now what I did was I rotated this, and now if I see very very clearly as to why I placed them in trans now, you can see that this particular bond has my OH, whereas this particular bond has my CH2OH. Now I can clearly see that these two groups, this OH and this OH and this CH2OH, are lying at the different bonding lines. So of course they are going to be trans with each other. Both are in opposite direction to each other, and thus I can clearly see that both of them, both of these will be trans to each other. And that is what I was after, as to why these two AOH and CH2OH in this cyclic structure that I have over here, why did I place them on transposition? So, drawing the Fisher form, I'm very, very clear about why I took them out and placed them in the transposition to each other. Because if I draw them, I can see that in order for these two to form the cyclic structure, because my lone pair of electrons are being transferred to my CHO group. So in order for this to happen, I have to make this structure, this particular structure, come in this form, and therefore I have got my OH and CH2O group in the trans form. Now, a few pointers about both the cyclic forms. So, I have named them A and B. What I can infer right away from this, that we had done a topic called hemiacetals. So, in hemiacetals, what I was emphasizing on, that a hemiacetal group has to have a, which groups it had? It had an OH group, also it had an OR group and an R group. Okay, so I had to have an alcohol, an ether group, an R group, and of course an H group. So I had these four groups, and whenever I see them appear on one carbon, I call it hemiacetal. So if I look at these two structures here right in front of me, now can I call this glucose a hemiacetal? How? So if I look at this carbon over here, I can see that I have got an OH group. I have got an OR group. Where is that OR group? This is an O, and the rest of it, this whole thing is the R for it. Okay. So I've got an OR group too. Then the next requirement was an R group. So this is an R group. Okay. And lastly, I needed an H group. So I can see that this carbon over here has all these groups present. So can I call this a hemiacetal now? Of course I can. So if I look at this carbon, let's call it 1. Let's call it 1. I can call this as hemiacetal because the first carbon, I can say that, now I can easily say that C1 has all the groups. So I can, C1 has all the groups. So it makes my glucose a hemiacetal. So glucose is hemiacetal. Okay. Now I am assuming that you can also see that these particular four groups are also present in the other cyclic structure. So I've got R over here and I've got an OR group over here. Okay. So glucose is a hemiacetal. Now what next? What I want to see also, that the first carbon which is being formed, that is this C1 carbon that we are talking about so much, in this I can also see that the placement of the OH group, this and this, the point of difference between these two cyclic structures is this placement of this OH group. And I can say that OH and H are in different configuration at C1. So if I want to write, what I'm trying to say is that at C1, OH and H are at different configuration. And if you remember, there's one topic that we did called diastereomers, and inside that topic there was this category. Was the subcategory known as anomers, where only one carbon was differing in the configuration and the rest of the structure looked exactly similar. So now can I say that this C1 is also an anomeric carbon? So this my C1, please keep in mind that I'm talking about both the structures over here, because both of them belong to glucose and they're only differing at the positioning of OH group. So now I can say that my C1 over here is also an anomeric carbon. So at C1, OH and H are at different configuration. So C1 is anomeric carbon. And we also learned that wherever the anomer appears, that carbon is known as the anomeric carbon. So, having decided all this, I can just clearly say now that my A and B structures, so my A and B are anomers. Okay, so they both are anomers, and also because at C1 I can see a different configuration of OH at both the cyclic structures. Now I can therefore say that this D-glucose, what are we talking about? We're talking about D-glucose, and I can just say that my D-glucose is existing in cyclic forms, two cyclic forms, and both of them are anomers. Also, I can also say that, let us just write the conclusion, that A and B are also what they are. They are also hemiacetals, as we have seen, because they possess all the four groups that are required for a structure to appear as hemiacetal. So this, my glucose, is a carbohydrate which is, the cyclic forms are anomers, the A and B form are anomers, and A and B are also hemiacetals. Okay, so I can infer this from this. Now, next, this last thing that I want to tell you about a little, if I'm covering the cyclic structures, is that if I look at the open structure here, this is in very less percentage in existence when it exists with this cyclic form. So it is actually in equilibrium with these two forms. So these three structures are in equilibrium. So I have got an open structure over here. Okay. And I've got a cyclic form and a cyclic form. So I am saying that these three structures are actually in equilibrium with each other, and the cyclic form is more stable than the open structures because I'm breaking the double bond of the CHO group in this open structure in this cyclic form. Okay, so my cyclic, I concluded that all these structures are in equilibrium, and this open structure is very, I can say this open structure is existing in less percentage. So it is present in less percentage, is existing in less percentage because my cyclic structures are more stable. So I've got my cyclic structure are more stable. Okay. So open structure is existing in less percentage because cyclic structures are more stable. Why? Because this CHO group over here this double bond at CHO is breaking down into giving me 2 sigma bonds. So this pi bond is breaking down and giving me 2 sigma bonds. Okay. Also, if I look at the percentage where these three structures are in aqueous form, so in aqueous form, if I see, it exists in this open structure, exists in very less percentage, low percentage, almost like 0.2% of presence in an aqueous solution if I keep with the three of them, and the rest is cyclic. So if I've got a aqueous solution, there is very less percentage of open structure existing in it. Okay, so what did I do? Here a less percentage exists. The open structure exists in less percentage. So that was the part that we wanted to see.